everyone and welcome to Learning at 11th Hour. In this video, I'm going to show you how we can obtain the excitation table for a given flip-flop. At the longer run, we are going to memorize it, or rather it would happen intuitively. But how do we actually arrive at the excitation table? So if we know that, then it is okay if we don't memorize it because we can always derive the excitation table on the go. So, excitation, as in how are we going to excite our flip flop, or what are the inputs that we are going to provide to a flip flop? That is what it indicates. So, this is in context with uh, two things. One is we know our present state and we know our next state, and we know which flip flop we are talking about. So, say if it is the excitation table of SR flip flop. So we know that the two inputs to the flip flop are going to be S and R. So the question here is, for known present and next state, what should I excite my flip flop with? Such that for a given present state, I would get the given next state. So let's get into the process. So here I know the present and the next states, and since these are all single bits, the possible combinations are 0 0, 0 1, 1 0, and 1 1. What does this mean? So the first case is it says that the present state is 0, and because of some input that I gave to the SR flip flop, it got excited, and the next state is also 0. Now, when can this happen? So here we see that there are two possibilities of the next state being 0, right? So either there was no change, the present state is 0, the next state has become 0. So next state becoming 0 either because there was no change or because the reset input was high. Because after all, let's write out the characteristic table of the SR flip flop. So uh, this is the characteristic table. So Qn reset set. For 1 1 it is indeterminate. So we see that the Qn plus 1 could be 0 when the reset input is high, or Qn plus 1 could be 0 in case I had the 0 0 inputs occurring at the flip flop and the previous state was also 0, which is the case over here, right? So this possibility is going to occur in case my SR is 0 0 or my SR input is 0 1. So only when these two inputs possibly occur at the flip flop, it will excite the flip flop such that the present state is 0 and the next state is also 0. So I can combine these two. So this means that S has to definitely be 0 and R may be 0 or 1. So I don't care what R is. If S is going to be 0, even if R is 0 or it is 1, my next state is going to be 0. So therefore, I can write out this as 0, don't care. So I'm going to excite my flip flop using 0, don't care, so that the present state is 0 and the next state is also 0. Applying the same logic for 0, 1. So the next state can be high provided the set input is high. So only when S is high and the reset is low can this kind of a possibility occur. If the present state is 1 and the next state is 0, this means that the flip flop has been reset. So that's possible only when the reset input is high. Now, the present state is 1 and the next state is also 1. So that means either no change of state has occurred, which means the inputs to the flip flop could be 0 0, or since the next state is 1, it could mean that the set input was high and the reset input is low. So these are the only two possible inputs that we could give to the flip flop so that the present state is also high and the next state is also high. So I can combine the two inputs, and what I would get here is don't care 0. Why? Because S can be either 0 or 1, but R definitely has to be 0. In that kind of a situation, the present state would be 1 and the next state would also be 1 for the SR flip flop. So this becomes our excitation table for the SR flip flop. So moving on to the JK flip flop, we see that on the right hand side we have the characteristic table, and we are going to derive the excitation table for this. So here in the first case, the present state is 0 and the next state is also 0. This is possible only under two situations. One is if there is a no change kind of a scenario where Qn was 0, therefore Qn plus 1 is also 0, such that J and K are 0, 0. Or if K input is high, only then the next state will be 0. So therefore, combining the two possibilities, we get 0, don't care as the inputs that should be exciting the flip flop. Looking at 0, 1. So the next state should be high and the present state is low. So this is like a toggle kind of a scenario that's occurring here. So this could be one of the possible inputs that J and K could take up, 1, 1. Or the next state is in the set state. So therefore, we can say that the JK input could be 1, 0. Even in that case, the Qn plus 1 would be high. So combining these two together, we get 1 don't care as our scenario. On similar terms, looking at the third case, again, this is a toggle scenario that could be possible. So 1, 1 is the first possibility. The second possibility is that the next state is reset. So therefore, that is K is high. Now combining these two inputs, we see don't care 1 is the input that it should be excited with. Now, present state is 1, next state is also 1. So, therefore, no change scenario is possible. So, 0, 0. Or the output should be high, right? Qn plus 1 is 1 only when J and K inputs are 1, 0. So, looking at the two scenarios, 0, 0 and 1, 0, and combining the two, we get don't care 0 as the next situation. So this is the input that it could be excited with. So this is the excitation table of the JK flip flop. Moving on to D flip flop. Obtaining the excitation table for the D flip flop is quite a simple task in the sense that the D input and the next state Qn plus 1 are always going to be equal. So here, if we just write out 0, 1, 0, 1, just writing out whatever is there in Qn plus 1, that would hold good. So this forms simply the excitation table for the D flip flop. Looking at T flip flop, here again we have 0, 0, 0, 1, 1, 0, 1, 1. T is the input, and we need to find out what we need to excite this T flip flop with such that these are the present and the next states. So, looking at the first case, we see that there is no toggling that is happening. So, that means T input should have been 0. Similarly, in the last scenario also, T input should be 0 because no toggling occurs. Whereas in case of the second and the third case, we see that 0 becomes 1, present state 0, next state is toggled 1, and present state is 1, it gets toggled in the next state. So therefore, T input should be high. So this is the excitation table of the T flip flop. The excitation table and the characteristic tables will be useful for obtaining the flip flop conversions, which we'll be discussing in the upcoming video. I hope this video was useful to you all. Thanks for watching.